Hello, welcome back to the maintenance course. Today we have a fresh new lecture about the maintenance of repairable systems. So we have already analyzed non-repairables and now it's time to dive into stochastic processes to see how we can perform the maintenance of repairable systems. So stick around and thank you for watching. The table of contents for today includes 7 topics. Some of them will include knowledge of stochastic processes, so it's going to be a little bit of a challenging lesson, but in the end I hope it's a good challenge. And let us start the lesson by the beginning, of course, by the analysis of repairable systems, giving you an introduction to the fundamental concepts. In repairable system analysis, we care about the reliability of the repairable system that we are investigating. And to perform repairable analysis, we need stochastic processes knowledge. And we need fundamentally 3 random variables of interest: the local time, the global time, and the counting variable. And these 3 variables will enable us to represent point processes that will model the behavior of our repairable system. This contrasts with other methodologies, such as the methodologies within RAM analysis or non-repairable analysis. A parenthesis is important here because non-repairable analysis can also be used to analyze repairable systems. If you take each time between failure and sees it as an independent system, you can analyze a repairable system using non-repairable analysis. However, you will miss the connections, the interrelationships between the different time between failures, the different failure occurrences. For that reason, it is best to resort to repairable analysis when we are dealing with complex repairable systems. As usual, we have the assumptions of the lecture. So the first assumption that we need to make when we study repairable systems is that we care only about the reliability of the system. So the maintenance times are neglected. We don't study how the maintenance actually occurs, or at least the time that it takes to perform a maintenance action. The interest is instead on 3 components: the cumulative number of failures at each point in time, the local time, which means the time between failures, how long it lasts on average, or for a specific failure, the time between failures. And the interest is also on global time, so from the start of the operation of the system until the failure, how long has passed. And these are fundamentally the 4 assumptions that we consider. A technique that is very useful and that I will use extensively in this lecture is the dot plot. And how do we construct a dot plot? Well, imagine that you have a system, a repairable system, that has 4 failures. And you can construct, draw the functionability profile of such system. Based on the functionability profile, we can construct a dot plot by ignoring the maintenance times. So, as I have said before, in reliability theory of repairable systems, we don't consider the maintenance times. We only consider the states of functioning. And we represent this in a dot plot with dots per failure and with a timeline. The underlying idea behind repairable analysis is very close to non-repairable analysis. Fundamentally, what we do is we analyze a series of systems, in this case repairable systems, and according to our observations, we try to predict what can happen in the future, and based on that we make maintenance decisions. Usually we try to keep track of 3 things when we are doing a repairable analysis: the cumulative number of failures, how many failures have happened until a certain point, the time between failures, and the time since start of operation for each different failure. And we need to keep track of this information, these three pieces of information, because they will represent random variables in our stochastic modeling process. So let us see in detail each random variable of interest, starting by the local time. So the local time is a way to represent the failures, and in this case the failure times are recorded as time since the previous failure until the failure E. Importantly, the local time at the first failure equals to the global time at the first failure. So these two random variables are the same for the first failure. But after that, we have to subtract one from the other. For example, to get the local time at failure 2, we need to subtract the global time at time 1 from the global time at time 2. And this makes sense. It's essentially to say, if I want to know the time between failure 1 and failure 2, I have to calculate the difference. And we also have the notion of global time, which is the time since the start until a given failure. And there is a correspondence between the global time and the local time. We can transform from one to the other. So for example, at the first failure, the local time and the global time is equally the same. But after that, you have to add up the local times to obtain the global time. So it's easy to see. If you have time between failures, if you add them up, you will get the global time. The third random variable of interest is the cumulative number of failures. So at each moment, I need to know how many failures have happened until that moment. And that is accounted with this variable. As I have already said, repairable systems have failures that can have some kind of connection or dependence between them. And we can identify two specific cases of that happening. The first one being deterioration, when the time between failures tends to get shorter with time, and the other one being the one of improvement, when the time between failures tend to increase and the system tends to be with a higher performance over time. In some literature, authors even refer to these two processes as the happy system and the sad system. So a system that is improving is a happy system, and a system that is deteriorating, they call it sad system. By using a dot plot, we can quickly see if a system is deteriorating or improving. So for instance, system 1 is clearly deteriorating. The time between failures are getting shorter over time, while the second system is clearly improving because the time between failures are increasing. And you may ask, why would the system improve in terms of performance? Well, if you're doing the maintenance correctly and improving even the performance of the system, you can see improving systems. The third system, finally, is an example of a system that has no clear pattern, but where the failures might be dependent on one another. And let us now start with the second section about the point process. And what is a point process? Essentially, a point process is a set of points, as simple as that. And those points are scattered randomly across a mathematical domain, for example, the real line or the Euclidean space. I will give an example from demographics that uses point processes for the Euclidean space. So imagine that you have a region and you want to see or you want to simulate or you want to study how houses are dispersed, are spread around a certain region. In that case, you can use a point process that is completely random, that we call complete spatial randomness, and you will have a result similar to the one that you see here. But you may think, houses are not uniformly distributed in my region. They are more located in the center. So you can use, in that case, a Gaussian distribution. And in that case, we are dealing with Gaussian spatial randomness. You could use a normal distribution with a larger standard deviation or a smaller standard deviation, and that will change the concentration of your houses in the region. Another example related to this is when you use clustered point processes. Clustered point processes allow you to define where are the clusters of your points. And an example of a useful point process that does this is the Thomas point process. And this might create a more realistic dispersion of your houses in that certain region. As we have seen, point processes can be used to analyze spatial data like the location of the houses in a given region. But they can also be used for temporal data, and that is what interests us in this lecture. But before we proceed, I would like to make here a small parenthesis regarding the name point process. Some authors prefer to use the term random point fields and ignore the term process. We call it point process partly because it's a stochastic process, so it derives from that. But process means a progress or evolution or it implies gradual change. And essentially that is not what we are talking about in point processes. Because the idea is that discrete events will happen and that we are trying to capture their essence. So the idea is not of continuous evolution, but of discrete jumps, discrete spikes over time. And importantly, there is this big set that is the stochastic process world, and inside we have the point processes. And a stochastic process, as I said, in most cases represents continuous change, continuous progress, like for example the value of a stock price over time. In contrast, a point process is about specific occurrences, like when customers enter the supermarket store. So one gives us typically a continuous idea of what is happening. The other gives a snapshot at distinct points in time. There are real-life examples of the use of point processes to model temporal events over time. One example from biology and computational neuroscience is to model the impulses in the neurons using point processes. Another example from physics is to model the detection of radioactive particles using a Geiger counter, using again the point processes. And if you gather data about the arrivals of customers at the supermarket, you can model it, you can simulate it in a computer with a point process. A brief history of point process. Point processes theory started to be investigated around the 30s with the theory of stochastic processes led by, for example, Kolmogorov or Khinchin, Levy, Feller, among others. The point process itself, the term was recorded in a PhD thesis in 1943 by Connie Palm. He used the word Punktprozess, I hope I say this correctly, in German, to define the term point process. The idea was polished by other mathematicians after the World War II, like Feller again and Wally Smith, and research today that involves point processes are like, for example, demography, like we've seen in the example before, population studies, and other fields like, for example, insurance. A point process can be represented in one of three ways, either by the local time variable, by the global time variable, or by the counting random variable. In either case, you can simulate your point process using information of that random variable alone. Perhaps the most important representation of a point process is the counting process. And I have here an example of a counting random variable for a given system. And you can see here that the function, the random variable, is always non-negative because it doesn't make sense to have number of failures that are negative. It's integer value because we are counting the number of failures over time. And it's increasing because we are accumulating the number of failures. So it has a tendency to stay the same or always increase. And this stochastic process counts the number of occurrences, or in our case of failures, as time goes by. And I'm going to discuss now three properties of point processes that are of utility. And the first one has to do with we having an interval from the beginning of the lifetime of the equipment until that specific time, let's call it V, and I want to know how many failures occurred there. If I know that a failure has occurred afterwards, then I know failure E, then I know that the number of failures that occurred before the V has to be smaller than E. But what if my V, my specific time that I'm interested in, happens after the failure E? Then in that case I know that I will have either E failures or more than E failures. So far I have been talking about intervals of time that cover since the beginning of operation until a certain time point. And what if I wanted to check the number of failures within a given interval? That could be anyway along the timeline. In that case, I can subtract the number of failures of W minus the number of failures at V, considering that my interval is from V to W. If I know, for example, that in my interval I will have a failure E, for example, failure 7, I will know that my number of failures at V will be smaller than 7 for sure, and that the number of failures at W will forcedly be more or equal to 7. And we end this section with the notion of increment. It's a very useful notion, as we will see, because it allows us to characterize the repairable system behavior and to select the best suitable option to model it, to select the precise point process that will be more suitable for the system. And an increment is nothing more than the number of events in a given interval from A to B, and you calculate it by subtracting the number of events at A from the number of events at B. So, for example, if you are interested in the number of failure events in the interval from 5 to 8, we subtract 2 from 3 and we get 1 failure event. Importantly, there's a distinction between the random variable n of t and the concept of increment. So the n of t is the number of failure events in an interval, but it's a different interval. It's from 0 to a specific time. So from the start of operation until a specific time. So the increment can slide across the timeline while the NFT is always connected to the point zero. Let us now discuss the mean cumulative function and why do we even need this tool. In reality, what happens is that we have the profile of several repairable systems, several graphs of the counting variables that are associated to each system. And looking at all of these graphs, especially if you have a high number of systems, is quite tedious and quite difficult. And one way to analyze them in a quicker way is to use the mean cumulative function, which is basically to average all of those curves into a single one. In formal terms, the mean cumulative function is the expectation function of the counting random variable, which is essentially the expected value of the number of failures through a specific time. This function is forcedly non-decreasing, it's a monotonic increasing function, because of course the counting random variable is also increasing, as we have seen. So we have here an example of the mean cumulative function, and we can see two systems here. They are represented by their counting random variable, and they are the red one and the gray. The mean cumulative function is the average value along the dimension of time, and we can see it here represented by the blue line. The mean cumulative function can tell us a lot about the behavior of the general system that we are observing, such as, for example, if it's concave down, we know that the system is improving because the time between failures are becoming longer and longer. In contrast, if we have a mean cumulative function that is concave up, it's getting steeper, then the system is worsening and it's deteriorating. If we have a straight line, it indicates that the number of failures is staying more or less the same over time. And we are now in section 4, where we will discuss a new topic that is the ROCOF function, or also called the intensity function. And I will try to motivate for the utility of this function. And let us remember non-repairable systems. So non-repairable systems which are discarded after a single failure, they might be replaced. We can use statistical distributions and the hazard function to analyze their behavior and set hard time fixed intervals of maintenance. Repairable systems are a different story because they recover from failure, so they have to be analyzed in a different way. And a tool to do that is to use the ROCOF function. And while the hazard function and the distributions in non-repairable analysis allows us to give a snapshot of the risk at each time, the ROCOF function gives us a different perspective about the ongoing trajectory of reliability of the repairable system. And what is the ROCOF, or as we call it, the rate of occurrence of failures function? Well, it's the derivative of the mean cumulative function, which gives us essentially the rate of change of the failures. And this rate of change allows us to check if the system is constant or if it's increasing or decreasing in terms of failures at different periods of time along the real line. And I'm going to show two examples, one of deterioration and one of improvement of repairable systems. And I can check if the system is deteriorating or improving just by looking at the mean cumulative function or to the ROCOF function. Looking here, I can see that this function in particular, this mean cumulative function, is concave up, so the system is deteriorating. But if I look at the ROCOF, it also tells me the same story, because the rate of change of failures is increasing. Then I have another example of a function that is concave down in terms of mean cumulative function. And I can see immediately that the time between failures are becoming longer and longer just by looking at the mean cumulative function. The same information is displayed in the ROCOF because I know that my rate of change is diminishing, so I'm getting less and less failures over time. But if we have the ROCOF, we also have the concept of intensity function, and I've talked about these two concepts. What is the difference? Well, there is no difference, it is the same, it's just a different formulation. So the intensity function is the probability of failure in a small interval divided by the length of the interval. So it's to consider the risk of any kind of failure, not necessarily just the first, of happening in that very small interval. And when we have a large intensity, we know that we have the probability of having many failures over the interval. If you have a small intensity, that's the opposite case. So if we have the bathtub curve for the non-repairable systems, we also have another bathtub curve for the intensity function of repairable systems, because essentially the behavior of a system is always the same. It goes through infant mortality, then a period of random failures, and then essentially in the end it starts deteriorating until its end of life. So now we are at the fifth section of our video, and we will cover the topic of increments. So let us see in more detail the implications of having certain increments. And I would like to start by the property of the independence of increments. And what does it mean to have independent increments? Well, essentially it means that the two intervals that you can place anywhere you want along the real line will not affect each other in terms of number of failures. When there are dependence among the increments, there are two possible types of dependence. The weak dependence, and it means that the previous interval affects me. So what happens immediately before affects me. That's weak dependence. And strong dependence means that very historical events in the past will affect me also. Importantly, the increments can behave similarly or not. So two distinct increments, so number of failures in different intervals, can follow the same distribution, the same statistical distribution or not. If they follow the same distribution, we call them stationary. Non-stationary increments are increments that behave according to different distributions. The distributions could even be from the same family. So, for example, they could be two normal distributions, but one is parametrized in one way and another in another way. In that case, we have non-stationary increments. And let us now look at different models that can be used to simulate and to capture the reliability of repairable systems. We have already discussed the concept of intensity function and how it characterizes the behavior of a given system. But we now need to introduce a new concept, which is the concept of repair or maintenance action. Because since we are talking about repairable systems, they will be repaired. And once a repair is done, it can change the intensity function. And we need to be aware of that. There are three possible cases of repairs. The first one being the perfect repair, or as good as new. And this means what? That I have my intensity function. It may be deteriorating or improving or constant. And when the perfect repair occurs, it puts the system back to its original state at the beginning of the operation of the system. So this is the perfect scenario in the scenario where we all wanted to live. Examples of this is when you replace a system by a new one. Sometimes it's not a perfect repair, but it's close to that. Or if you do, for example, an engine overhaul, which is a very extensive and comprehensive action that tries to put the system as much as possible back to its original condition. And then we have the concept of minimal repair, which does nothing to the intensity function. So imagine that you are having more and more failures, you'll continue to have more and more failures. Or in the other case, if you have less and less failures, you have less and less failures in terms of intensity function. So in that case, a typical example is the tire of your car. So if you imagine that you have a flat tire, this does not affect the reliability of the system, but you need to do some kind of intervention, some kind of repair, and that's called minimal repair. Everything that's in between perfect repair and minimal repair we call imperfect repair. So to summarize, if you have a repairable system, you will have failures, and you need to repair them. Regardless of the maintenance strategy to identify the failures, you will need to perform a repair. And the repair can have different impacts, and according to the impact, we can classify it as perfect repair, imperfect, or minimal repair. To model the behavior of repairable systems that have perfect repairs, we can use renewal processes or generalized renewal processes. And for that, we need to guarantee that the increments are stationary and independent, and that there is kind of like a reset of the distribution after an arrival epoch. Essentially, the distribution is the same before and after the arrival epoch, and the increments are independent, of course, because what happens in the past does not affect the future. But essentially it is, they can model the reset of the behavior of the system. Poisson processes can be considered renewal processes because they have a constant intensity function, so they can be considered to have perfect repairs. Minimal repair processes involve increments that are non-stationary to allow us to continue the distribution and not resort to a new one, a copy of the previous one, and it involves always independent increments. An example of a minimal repair process is the non-homogeneous Poisson process. It respects the properties of independent increments and non-stationary. It's essentially a Poisson process where the intensity function can vary with time. And then we have the concept of imperfect repair, in which we assume that the maintenance action does not put the system back to good as new, but only a little bit younger. So, for example, an engine wash is an example of an imperfect repair. To analyze this kind of repairs, we have to resort to more complex, more advanced topics, such as the process Kijima type 1 and 2, and we need to introduce the concept of virtual age. We are now at the 6th section, and we are going to discuss the topic of Poisson process or homogeneous Poisson process. So the homogeneous Poisson process is very useful because it needs little information and it can be applied to a variety of situations. So what do you need to know to apply a Poisson process? Essentially, you need to know the average number of events that occur in a given interval of time. And if you know this, you can model the system as a Poisson process. When we are dealing with the Poisson process, we can be sure of three things. The first thing is that the number of events, or the number of failures, is zero at the start. The second one is that because the intensity function is a constant, as we will see, the events are independent of each other, and they're also stationary because of this. Importantly, the Poisson distribution probability mass function has this shape, and it gives us the probability of observing a certain number of events in a given period, given two parameters. You have to pass to the function two parameters, the length of the period that you observed and the number of events that you observed during that period of time. You can simplify the fraction number of events over interval of time into the parameter that we call lambda, that if you make the calculations you can see it's going to be equal to the intensity function. So we have a constant intensity function equal to lambda. The lambda is also the mean number and the variance of events in the interval. And it is time to say goodbye. I hope you have enjoyed the lecture. It was a little bit challenging, but I think it was worth it. Thank you for watching and see you next video.